This is a tuba. This is an instrument used in concert bands and orchestras, and it may be something that some of you have played before if you were involved in band or orchestra in high school. This particular instrument is about 20 years old and was manufactured in Germany by a company called VMI. Let's give a demonstration of how it sounds. That was an A that I finished playing there. The range of this instrument is pretty good. Bottom note wasn't very in tune today. It's a little bit warm in my room here. So this is one instrument we call a tuba. This is also a tuba. This tuba here is actually a brand new horn that I've had about maybe a year or so, made by a company called Wessex. And this is what's referred to as a travel tuba. The tuba itself here has essentially the same abilities as the larger horn, it's just smaller. This particular horn will actually fit in the overhead bin on an airplane, making it convenient for professional players to travel with this particular tuba for practicing purposes. The tone is a little bit different. Let's hear how it sounds. This horn also has somewhat of a different range to it. Very small, different horn. This is an instrument called a Helican. This happens to be the oldest instrument in my collection, being manufactured around 1902. This particular instrument was used as a predecessor in marching bands to the sousaphone, which is more common today. And it has a rather unique history to it. Originally, when I obtained this horn, it was what was referred to as a low-pitched horn. Prior to the Treaty of Versailles, there was no standard pitches for band or orchestras. The Treaty of Versailles standardized the tuning pitch that the note A has a frequency of 440 Hertz. This is the note that you have heard being tuned to if you go to an orchestra concert, typically played by the oboe. This particular horn sounds like this. Little different range because of how this horn was made. What I'd like to do with this video is show you how all three of these horns are actually playing the same note by taking a look at the frequency that is being generated by these horns using an oscilloscope. Let's take a look at it now. In our case, we're using a device from a company called an Analog Discovery. Now, an Analog Discovery is an oscilloscope, and it's got some other logic analysis tools and things we would need in engineering to try and figure out what's going on with the system. We're going to be using this very simplistically as an oscilloscope. So what we're going to do to begin with is we're going to start up our oscilloscope. So what we want is essentially here, oops, I'm on the wrong tab here. I want to start the oscilloscope running like so. And when I start it running, we're just going to see right now a bunch of garbage on the screen. The input, or the tone that is being generated in the background, is being fed into channel 1 here. Channel 2, you'll notice, is perfectly flat. There's absolutely nothing going on with that signal. So I'm going to turn off channel 2 so we're only looking at channel 1.
Now I can tell the way this is jumping around that probably my time and my level settings are not necessarily correct. So what I'm going to do is take and adjust the time here, which is essentially changing the scaling of the signal. So you see here how we got a closer view of it. This base value here determines what is the time difference between two of these vertical columns here, the vertical lines going up and down the scope. So the distance between here and here is 10 milliseconds. Now I'd like to kind of zoom this in a little bit more, so I'm going to set this to maybe be 5. And we'll notice it's still jumping a little bit. What I'm also going to do is I'm going to adjust the range, make the signal here maybe 200 millivolts per division. Now you see it still jumps around a little bit. I may adjust my trigger here a little bit so that the level is maybe a little bit down or a little bit up, and that may help to stabilize the signal a little bit. And now we're starting to get worse off, like so. And sometimes we can be successful with adjusting it, sometimes not. Depends on the type of signal we've got coming in. And what I'm going to do is get it up on the screen. I'm going to click on stop. Now stopping it, what that means is I have now taken a snapshot of the screen, a snapshot of my signal. And I would like to put on a device called a cursor. A cursor allows me to measure the time difference between two items. So in this case, what I'm going to do is put on a cursor, and I want to select this cursor here. Oops. Move this cursor so it lines up right with the peak of this point on the signal. You can see that this signal is kind of repetitive. There's a peak, there's a peak, there's a peak, there's a peak. Now I can take and turn on a second cursor, like so, and I can adjust it here to find that peak right about there. And if we look, we can see that the difference in time between this peak and this peak is 9.1 milliseconds. That's an important number because that time difference there tells me what the frequency is, or the fundamental frequency of this note. There's actually what we refer to as harmonics going on right now. The harmonics are why this is not just a nice sine wave. So if I want to figure out the frequency, the fundamental frequency between this point and this point and this point, I can calculate this based upon this number here. So if I take a calculator, and I drag a calculator onto the screen here, my time difference, I want to do 1 divided by 0.00911127. The value that I get is 109.7. 109.7 is very, very close to 110. Keep that in mind for a few moments here. Now we're looking at the waveform generated by the travel tuba, and you can actually see that to some extent this looks like it is a very, very similar frequency to what we had before. The other thing I'll note with this is that this seems to be a little bit more of a stable. We're not seeing it rolling back and forth quite so much. So let's take a look at what the frequency is here. So I'm going to stop this, and what I want to do is measure this bottom point here, and if I drag this around here, you can see I'm actually having to do very, very little change to it. Distance is 9.1031. If I do the same calculation, 1 divided by 9, whoops, I'm doing this wrong, 1 divided by 0.00911031, like so, 109.85. Very, very close frequency-wise. So we've been able to see that the Helican and the travel tuba basically are making the same frequency tone or frequency note. Let's see here the concert tubas. Now I'm going to take and stop this as well right here. And I want to drag. I'm going to look at what we have here. Zoom it in here so I'm down kind of at the bottom there. And as best as I can, get that down to the middle. So here to here, 9.1427 milliseconds. So if I do the calculation on this, 1 divided by 0.00911427, 109.37. So at this point, what we've seen is basically the pitch made by each one of these three horns has fundamentally the same frequency. The reason they fundamentally have the same frequency is because it is the same note being played by each one of them. The note that is being played is an A on the bottom of the bass clef staff. That note happens to be exactly 2 octaves below the typical tuning note A440. If you go to an orchestral concert, typically the oboe will play an A440 for the rest of the orchestra to tune. This note is exactly 2 octaves below that, which means if you take 440 divided by 2, you get 220 divided by 2 again, you get 110. We are very, very close to that 110 hertz frequency, indicating that all three of these horns are playing the same pitch. So this has demonstrated to you a little bit of how we use an oscilloscope to measure things, how we can go about taking measurements of things over time with an oscilloscope. I'm going to bring this video to a close.